In this video, we shall be solving the questions from NCERT textbook. The chapter is Magnetism and Matter, and as per the rationalized syllabus 23-24, the total number of questions which we are going to have here is 1 to 9. Earlier the number of questions were more, total questions used to be 15, but because some portions has been deleted, now the total number of questions are reduced to 9. So let us solve them one by one. Question number 1 is saying that there is a short bar magnet which is placed at an angle 30 degree with its axis in an external magnetic field. The strength of field is 0.25 Tesla and it is experiencing a torque tau is equal to 4.5 into 10 raised to minus 2 joule. The question is, what is the magnitude of magnetic moment of the magnet? So things which are given as input in the question is B, that is magnetic field 0.25 Tesla, inclination, that is 30 degree, theta is equal to 30 degree, and the torque is 4.5 into 10 raised to minus 2 joule. We have to calculate magnetic moment. As we know, the formula for the torque is tau is equal to mb sine theta. M value we have to calculate. Tau value is given 4.5 into 10 raised to minus 2. B is 0.25, sine 30, we have to take the value of sine 30 as 1 by 2, 0.25 we can take 1 by 4 to just get the value or simplified calculation. Now 1 by 4 and 1 by 2, it is nothing but 1 by 8 going other side and multiplying with 4.5, it is nothing but 36, and 36 into 10 raised to minus 2, it is nothing but 0.36 ampere meter square. Question number 2 is saying that a short bar magnet, the magnetic moment is given, is placed in uniform magnetic field. Field strength is given 0.15 Tesla. If the bar is free to rotate, the question is, which orientation would it correspond to stable and unstable equilibrium? When we talk about potential energy, if it is minimum, the magnet is stable. If it is maximum, the magnet is unstable. So energy wise, if we want to conclude, we can say minimum energy, stable equilibrium, maximum energy, unstable equilibrium. Formula of the potential energy, if we are going to use, we can use formula as U is equal to minus mb cos theta, and at the orientation when it is 0 degree, it is minimum energy and stable equilibrium. So if we put cos as 0, it is minus mb. M value is given as 0.32, B is given as 0.15 Tesla, so it is 0.48 joule. Similarly, if we take for the unstable equilibrium, the orientation is 180 degree and the energy is maximum, that is plus mb. Again, if we are going to put the value similar, that is 0.48 but with positive sign, is the answer for the unstable equilibrium. Question number 3, there is a solenoid having 800 turns and area of cross section is 2.5 into 10 raised to minus 4 meter square. The carries a current of 3 ampere. Question is, explain the sense in which the solenoid acts like a bar magnet. What is its associated magnetic moment? So what all things are given in the question? First, the number of turns 800, area of cross section, then current is given. First, the condition is being asked, explain the sense in which the solenoid acts like a bar magnet. We know that whenever there is a current through a solenoid, magnetic field lines would be linked with the solenoid. Outside from north to south, inside from south to north. And because of this magnetic field lines which is developing along its axis, it behaves as a bar magnet. Now the next part of this question is magnetic moment we have to calculate. So we know that the formula for the magnetic moment is I into area for one turn. There are many turns in the solenoid, so it will be number of turns into current into area, that is NIA. Now N is 800, I is 3, A is 2.5 into 10 raised to minus 4. Once we calculate, it is nothing but 8 into 2.5, it is 800 into 2.5, it is 2000 into 3, it is 6000 into 10 raised to minus 4, or 0.6 ampere meter square. Question number 5.4, that is question number 4, is saying that if the solenoid in previous question is to turn about the vertical direction and a uniform horizontal magnetic field of 0.25 Tesla is applied, what is the magnitude of torque on the solenoid when its axis makes an angle of 30 degree with the direction of applied field? So things which are given here is M, already we have calculated in the previous question. Then B, magnetic field is 0.25, theta is 30 degree. The question is magnitude of torque. So we know the formula for the torque is tau is equal to mb sin theta. M value we have calculated in 5.3 as 0.6. B is given 0.25. Angle up to which it is getting rotated is 0.30 degree. So it will be 0.5 or 1 by 2. So once we take 0.6, 0.25 is nothing but 1 by 4, sine 30 is nothing but 1 by 2, so it will be 0.6 upon 8, or the torque experienced by this particular solenoid is 60 upon 8 into 10 raised to minus 2, or 7.5 into 10 raised to minus 2 Newton meter. Question number 5, it's saying a bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of uniform magnetic field 0.22 Tesla. A. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment? Number 1, normal to the field direction. Number 2, opposite to the field direction. And B part, what is the torque on the magnet in both the cases? So things which are given here is magnetic moment is given, then B, that is magnetic field, is given. Theta 1 is 0 degree. What we have to calculate actually in one, normal to the field direction. So theta 1 is equal to 0, normal means perpendicular, theta 2 is equal to 90 degree. So once we take theta 1 is equal to 0, theta 2 is equal to 90 degree, we will be calculating the work done by taking the formula mb cos theta 1 minus cos theta 2. That is the potential energy or the work done in rotating a particular dipole. Once we put all the values, m as 1.5, b as 0.22, cos theta 1 0 degree, theta 2 90 degree, and we calculate cos theta 0 is 1, 90 is 0. So 1.5 into 0.22 it is nothing but 0.33 joule will be the work done in case A when it is rotated normal to the field direction. Now when it is rotated opposite direction, that is 0 degree to 180 degree, theta 1 is equal to 0, theta 2 is equal to 180 degree. In that situation the work done remains mb cos theta 1 minus cos theta 2. If we put the value of cos theta 1 as 0 degree, cos theta 2 180 degree, cos 0 is 1, cos 180 degree minus 1, so it will be minus 1 minus minus plus 1, it is equal to 2, and after getting multiplied it is nothing but 1.5 into 2, that is 3, into 0.22, it is nothing but 0.66 joule. Next part in the B, it is being asked in each case what is the torque experienced by the magnet in case 1 and 2. So torque formula is again mb sin theta sin 90. We know it is maximum and 1. So 1.5 into 0.22 into 1, the torque would be maximum and it is 0.33 Newton meter. In second case, when it is angle is 180 degree, 180 sine, with sine it is 0, so there is no net torque experienced by the magnet and it is equal to 0. Question number 6, there is a solenoid, total number of turns is 2000 and area of cross section is given. So what is given part, if we are going to have the n is equal to 2000, area of cross section is given, current is passing 4 ampere, suspended through its center allowing it to turn in a horizontal plane. What is the magnetic moment associated with the solenoid? So B is given, magnetic field is given as per the B part. Let us first calculate A part of this question. So A part is the magnetic moment. Formula is NIA, and N is 2000, I is 4 ampere, area of cross section if you are going to put, and on putting all the values, it will be coming as 1.28 ampere meter square. Now B part, what is the force and torque on the solenoid if a uniform horizontal magnetic field of 7.5 into 10 raised to minus 2 Tesla is set up at an angle 30 degree with the axis of the solenoid. So B is given and the angle is given. We have to calculate the torque. Formula is mb sine theta. If we put m as 1.28, b as 7.5 into 10 raised to minus 2 and sine 30 as 1 by 2, after calculation we will be getting the value of torque as 0.64 into 7.5 into 10 raised to minus 2. 0.64 on multiplying with 7.5, it is nothing but 4.8 into 10 raised to minus 2 Newton meter. Question number 7 is short bar magnet has a magnetic moment 0.48 joule per Tesla. So M is given 0.48. Give the direction and magnitude of magnetic field produced by the magnet at a distance 10 centimeter from the center of the magnet on axis and equatorial line. So basically we have to calculate the field at end-on position or axial line position and broad-on position or equatorial line position. So formula for that we are going to have here. What is B at equatorial, what is B at axial, we have to calculate. The formula, once we calculate the field at the axial line, is nothing but mu naught upon 4 pi 2 into magnetic moment upon distance cube, that is r cube. So mu naught upon 4 pi 10 raised to minus 7, 2 m value 0.48, and 10 centimeter distance we have to change into meter as 0.1 after getting it cube, and if we simplify it, it is nothing but 9.6 into 10 raised to minus 5 Tesla. We are going to calculate the value at broad-on position or equatorial line position. We know that at equatorial the field is just half, so directly also we can write the value as 4.8 into 10 raised to minus 5. But let us calculate mu naught upon 4 pi m upon r cube. 10 raised to minus 7, m is 0.48, r is 0.1 cube, and 0.48 into 10 raised to minus 7 into 10 raised to minus 3 will go up, it will be 10 raised to plus 3 because 0.1 is nothing but 10 raised to minus 1. On calculation it is 4.8 into 10 raised to minus 5 Tesla. In this question there is a bar magnet, short bar magnet, and it is having an axis, and there is a null point obtained on its axis at a distance 40 centimeter. As we know that on its axis there will be the field, that is magnetic field, how much? B is equal to mu naught upon 4 pi 2m upon r cube. But as per the question, null points are found on the axis of the magnet at 14 centimeter from the center of the magnet. So at a distance 14 centimeter, field is there. Null point means total field will be equal to 0, and that is possible only if there is another field encountering the field of the bar magnet. So that field is nothing but the magnetic field of the earth in the direction opposite to the B axial, that is magnetic field at axial point by the bar magnet. So if we see here, axial is equal to magnetic field of the earth is equal to 0.36 Gauss as per the question. Now the question is, what is the total magnetic field on the normal bisector of the magnet? So normal bisector means this particular part, and normal bisector means end-on position also we can say. We know that at normal bisector or at any point on its equatorial line there will be two fields, four components, two same would get cancelled, and then net field will be obtained in this direction. And one more thing we know, that the relation between axial and equatorial is differed by 2 or the factor of 2. So B axial is equal to 2 into B equatorial, or equatorial is equal to half to that of the axial. So half means it will be 0.18 Gauss, but this is not the total field at that point, because Earth magnetic field is present at each and every point, having 0.36 Gauss in magnitude. So already we have calculated 0.18 Gauss because of the magnet itself and being supported by the Earth magnetic field. So total field would be added by the equatorial plus Earth magnetic field. So Earth magnetic field is 0.36. Equatorial we have calculated 0.18. So after getting it added, it is 0.54 Gauss as the total magnetic field at equatorial line position. Question number 9 is saying that if a bar magnet in the previous question is turned by 180 degree. So this was the condition of the previous question. We are going to turn the magnet by 180 degree. What will happen? Both the fields would change its direction. First, the axial will be in the direction of the field or the earth magnetic field. So there is no chance to get any null point on its axial line position. Now where is the chance? So at equatorial line position, the field again is going to reverse. It means if the equatorial line position field created by the magnet is going to encounter the field created by the earth or a field existing by the earth, there is a chance to get the null point. So if we take the mathematical calculation here, axial value is equal to magnetic field of the earth as per the first condition, and then equatorial value also must be equal to the magnetic field of the earth, so that we can get the another null point. We have the formula as mu naught upon 4 pi 2m upon x cube, that x is already 14 centimeter. Let us consider that from the center of the dipole the distance of equatorial point is y. So what is the field? Mu naught upon 4 pi m upon y cube. If we are going to equate these two, we will be getting this equation, and after simplifying, the equation which we are going to get here is 2 upon x cube is equal to 1 upon y cube, or next equation which we are going to get, y upon x whole cube is equal to 1 by 2, or y upon x is equal to 1 by 2 cube root, or 1 by 2 whole power 1 by 3, or y upon x is equal to 1 by 2 to cube root, it is nothing but 0.794, or y is equal to x into 0.794, x value is 11 centimeter, sorry 14 centimeter. If we put this value, we will be getting final answer as 11.1 centimeter. So at the distance from the center at equatorial line or at perpendicular bisector 11.1 centimeter, there will be another null point for the new case. Thanks for watching.